Hello, my name is Ralph Grundler. I'm the Senior Director of Marketing at FlexLogix. This is Reconfigurable Computing with analog chips and MCUs for rapidly changing markets. There's one thing we can agree on is that analog interfaces and MCUs are everywhere. I would even say ubiquitous. We know that analog interfaces with microcontrollers are being used in remotes, automobiles, factories, medical devices, and satellites. There are more than 50 in each house, hundreds in a car, and thousands in a modern factory. Almost every electronic device you have touched has some kind of MCU or analog. There are more than 5 billion microcontrollers are being added to our world every year, and it is growing. If we take a look at just one application like a modern home, we can see how this can be. MCUs and analog interfaces at home. There are many possible uses for MCUs and analogs in a standard house. Some examples are security cameras, lighting control, smart speakers, voice remotes, fire CO2, even smart toilets, garage door openers, dishwashers, a robot. Well, I don't have a robot yet, but someday I'll have a cleaner robot that's better than the Roomba. But there are multiples of MCUs and analog interfaces in many of these devices as well too. So, well, what if you had one SoC that could be used for all of them, or at least multiples of these applications, adding flexibility at a low power and cost and make this a reality? Let's take a look at a simple MCU analog system. Most analog MCU chips have a small amount of digital circuitry. These designs can be very simple, but the growing concerns of security, localization, and increases on complexity are creating a demand for more logic, with more flexibility at a lower power and, as always, a reduced cost. TSMC 40 nanometer and other TSMC nodes are perfect for this type of application and small chip with specific analog functionality, but the question is how to add flexibility and still meet all the cost requirements. Simple. By adding a small eFPGA or embedded FPGA in the design, the engineering team can meet the requirements of low power and lower cost, yet provide acceleration to critical system actions. By leveraging TSMC and other TSMC technologies, including an eFPGA, will reduce the power and cost of the system and provide the flexibility needed to the end customer. With eFPGA design, you can go in any direction and support multiple applications for acceleration for use in different systems. Another application is the use of MCUs in factories. Factories are installing industrial robots, automated guided vehicles, collaborative robots, and smart sensor assemblies. These real-time applications need designs to achieve high performance, yet at a smaller footprint and energy efficiency. Hardware can reduce the software latency by 100 or even 1,000 times, improving performance, and implementing an eFPGA meets all the requirements of a smaller footprint and energy efficiency, with the extra benefit of providing the flexibility to update in the field, or in this case, in the factory. This applies to other applications that require hardware performance and need flexibility in their usage model. There are many different functionalities that can be added into an eFPGA to provide system flexibility. Different applications can benefit from flexible hardware, acceleration for filtering, acceleration for encryption, different types of monitoring, security, and machine learning. All these can be put inside an eFPGA. In fact, the number of applications for the FPGA is just limited by the imagination of the engineer. And even some SoC vendors could create a library and provide those to their end customer. Hardware accelerators for MCU and analog. We think of the eFPGA as an extension of the MCU analog part. This can be naturally extended to a library that can be offered to customers, increase the SoC value to them as well too. There are many functionalities that we can add to an eFPGA, and we'll review some examples of an I/O peripheral, flexible functionality, and also some encryption flexibility. If the chip is pin limited, one example here is by reconfiguring the different functionality through the same pins can increase the design's target market. Also, there's also the possibility that there's some error or that your customer may need one additional function, maybe a parity bit or something that's missing in I2C or SPI. It's easy with an eFPGA. You just add it into the eFPGA and it'll satisfy your customer's requirements and you can ship the product. Also note that the APB interface is small enough to fit. It's just a few hundred LUTs. It'll fit in the eFPGA, and that allows flexibility as well too, so you can connect to maybe a high performance part of the system or sideband bus to the processor. In some cases you might need even more I/O flexibility. Reconfigurable I/O function. The possibilities are endless, but a simple example is using the eFPGA for different types of I/O interfaces. The beauty here is the simplicity of the design, which can be pre-baked or customized for the end user. This also allows for different permutations of UARTs and GPIOs or other functionality that is needed by the customer and needs to be accelerated. These can even be reprogrammed dynamically as fast as a few millionths of a second. We're talking microseconds here. The system can respond to the input and be reprogrammed like in the next example that I have. eFPGA is excellent as a reconfigurable coprocessor, and reprogramming dynamically in millionths of a second allows the system to react to the input for different applications. The eFPGA design can offer the flexibility of software, but the acceleration of hardware. For example, we have three scenarios here where a customer has programmed the design. In scenario 1, the ES encryption was used in one configuration and LZW compression was used in another configuration. In scenario 2, they added more eFPGA and used SHA encryption and LZW compression compared to a 1 gig, 10 gig, 4-channel network stack. In another scenario, scenario 3, customer used SHA encryption, LZW compression, and then SHA encryption with AES encryption. So there's all kinds of different ways you can mix and match these designs and reprogram dynamically. An idea that customers can do is pre-package these designs in a GUI for ease of implementation. So a GUI supporting a library of functions is something that the customers, I think, would really appreciate. By pre-engineering the functional blocks and testing everything before it gets to the customer, we know everything is working and intact. This MCU template shows the eFPGA either connected to the AHB or the APB, and either one is possible just based on configuration. But the template could also show the eFPGA connected to the MCU on a sideband bus for even higher performance. This is pretty straightforward for the customer, and their basic flow would be click and drag into the design, enter in the system addressing, and program the part. Click the programming part button. There are customer examples of how they've implemented this, and I'll show that on the next slides. This example, a customer had a dual processor system. In fact, this example uses dual ARM7 processors with a 1x1 eFPGA for reconfigurability of internal IP connections and implementing the custom hardware blocks. With some fixed blocks, the eFPGA can be reconfigured with AHB, SPI, JTAG protocols, or used for hardware-based CRC, or acceleration of software-based encryption. So it has three different functionalities, and we'll see that on the next slide. These three different examples, this dual processor provides flexibility to the system. So for example, in the first example, it's an accelerator with I/O functions, and in this case AES, UART, I2C, and HDLC. And then in the second example, it's used as voting logic for dual-core processors running in lockstep. And then in the third example, there's specific I/O tasks that each one of the processors is dedicated to using, and the eFPGA is tied with those processors. So you can see there, this flexibility provides a lot of benefit not only to the end user, but also to the person who created the chip, because then they can use one chip for multiple different applications. So you might ask, what are the benefits of integrating an eFlex eFPGA? And there's lots of different benefits to the SoC. It has it programmably like a CPU or DSP, but parallel processing power and speed, which is like hardware. And like a CPU, it's reprogrammable anytime, saving mask respins, or you could do updates in the field if needed. And if you don't want people to know what is in your eFPGA, it can be made secure, yet save power and provide future flexibility. Saving the total system power is one of the most important benefits. Save power, integrate FPGAs. Anytime it's possible to integrate a chip, the system will save on power. By reducing the number of high-speed SerDes or other interfaces, the FPGA will use less power, reducing system costs, reducing testing time, manufacturing failures, less products to inventory, as well as system performance benefits. CPU talks directly to the eFlex eFPGA. By talking directly to the eFPGA, there's no need to go off-chip or on-chip via high-speed, high-power SerDes, therefore not only reducing the latency, but also reducing the power usage during any kind of communication. So therefore, on-chip communication reduces latency. Skate designs with eFlex eFPGA. One way to keep your designs confidential is through obfuscation. Simply don't program your secret design into the SoC until you get it back from manufacturing. Then the next question is, how do you make sure you have the right size for your eFPGA? And this is solved with software. To match your applications, by including only what is needed into the system, you can save on area, power, and cost. FlexLogic's GUI tools help the designer easily design and integrate a high-speed accelerator. This effort of saving reduces the schedule by including an eFPGA. So again, the right size is what really saves on area, power, and cost. But there are other things that you can do as well too to the design. So by future-proofing the SoC, you can design an SoC with eFPGA or without eFPGA. The schedule is basically the same. The advantage is that you have some amount of RTL that you can change anytime. And this is really helpful should you need some kind of system fix or some kind of bug that need to overcome. You can really future-proof your design by reprogramming anytime. Another great example of eFPGA use is increasing the configurability in target markets. So having the same SoC work in multiple regions is very beneficial to reduce the cost and increase the flexibility for changing regional requirements. One chip is used worldwide even though each country has different specifications and requirements which are modified to best serve those markets. There are other ways also that the eFPGA can be implemented. eFPGA chiplets provide rapid solutions. In some cases, the eFPGA is fixed for several designs, but the analog might be in different technologies. One solution is to make the eFPGA into a chiplet. Leveraging the technology with TSMC is what makes this all possible. The secret to an excellent eFPGA solution is the eFPGA interconnect inside the eFPGA, and we'll discuss this on the next slide. One distinct advantage of eFlex is its smaller, faster interconnect, and it's designed for IP integration. So FlexLogic patented interconnect network technology allows the use of standard cell logic process at a similar performance and density to customized FPGAs, making embedded FPGA applications simple and cost-effective to be included into an SoC. This interconnect results in some of the highest utilization in the industry, with many projects easily reaching over 90% utilization. So even more impressive is the design is based on standard cells, making it easy to implement and quickly for us to port. We have ported to several different TSMC processes. eFlex eFPGA technology is available in several TSMC technologies. Other technologies can be ported quickly, and 5 nanometer is next. The elegance of the eFPGA design is that it's implemented in the lower metal stacks, resulting in the most metal stack coverage and support of any eFPGA vendor. This allows the design to be used at almost any of the popular metal stacks in each technology. TSMC silicon proven. eFlex eFPGAs are silicon proven with test chips that are characterized on evaluation boards. Through silicon characterization and verification is why every FlexLogic customer's tape out is successful. Silicon proof is why customers go with FlexLogix and TSMC. Here we show 3 different examples in TSMC 40 ULP and LP, 28 HPC, TSMC 16 FFC and FFC Plus, as well as 12 FFC, and TSMC N7 nanometer test chips. One eFPGA provider. Join the #1 eFPGA provider like the customers listed here and many others not. More than 16 chips working in silicon, 14 in design, and another 25 being designed. We've become the most broadly available eFPGA company with designs from 180 nanometer to soon 5 nanometer. Why is that? Because systems need reconfigurably, want to save power and cost with an easy to implement solution that is proven in silicon. Thank you for watching this presentation, and feel free to contact me with questions at ralph@flexlogix.com. Thank you.